Joe Kelly could throw a 95-mile-an-hour curveball, which is pretty amazing when you think about it because that's pretty fast. Anyway, so if we were to try to analyze how far away from the plate, if the ball starts on this side of the plate, how far does the ball move across the plate before the batter gets the swing out of it? Well, we're going to call that this particular direction. We'll call that Y. So how far did the ball move once it left his hand, and then the catcher catches it over here? Well, there's a formula for the Y, and that Y is going to be equal to the R minus R squared minus D. Well, D is right here. It's 60.5 feet. R is going to be the radius of that curve. All right, so we need to find the radius. We know the distance, so the main thing we want to do is find the radius, then we can find Y. If he throws it 95 miles an hour, that's about 139.3 feet per second. So that's going to be coming in the X direction. And it's going to be along this line, lining up with the plate. So when the ball leaves his hand, it's going to end up taking a curved path, so it's going to end up on the other side of the plate. And that's what he wanted. He wanted the ball to look like it's going to come across this side of the plate, but it actually is going to end up over on this side of the plate. So there's a thing that's called Magnus effect. When the way the pitcher makes the ball rotate, it causes the stitches in the ball to dig into the air. That causes high and low pressures. Those high and low pressures cause the ball to curve. And that's what he wants. He wants the ball to curve. Well, that particular force is called the Magnus force. All right, so it depends on a lot of things. It depends on how many rotations per second. It depends on velocity initial, how fast a person can throw it. It also depends on air pressure. It depends on air density. There's a lot of things it depends on. But anyway, a 95-mile-an-hour curveball is going to, generally speaking, give you a Magnus force of about 0.2 pounds. So when the ball leaves the hand of the pitcher, it's spinning, and those stitches are digging into the air and they're causing high and low pressures. It's going to make the ball move. It's going to move with a 0.2238 pounds. So the ball is going to feel a force pushing it over in this direction of about 0.2238 pounds. All right. It's interesting to realize that baseball is mostly played in the United States, so we're going to be using pounds. And pounds is slugs, feet per second squared. Okay, so your slugs is your mass, right? Feet per second squared is the pull of gravity. So this is MA. All right, so my force is equal to MA. It's important that you realize that because we're going to look at slugs here in a little bit. All right, so number one, let's look at how much time it takes to go from here to there. It's going to be important to know sooner or later down the road. Simple equation. Velocity is distance divided by time. Time then, therefore, is distance divided by velocity. We know the distance, 60.5 feet. We know the velocity. That comes to about 0.434 seconds. All right? So that means if you are a batter in the Major League Baseball and you're facing Joe Kelly, you have about 0.434 seconds to make up your mind if you're gonna hit that ball. Maybe some of the mechanics of what Joe Kelly did, you might be able to know what he's going to throw. Maybe, maybe not. So that's probably why most batters are in the 25 to 27% of the time they hit the ball. That means almost 70% of the time they're not hitting the ball. So that people in the outfield 70% of the time are not defending anything. So that's why Joe Kelly with the 95-mile-an-hour curveball was really important, because you want to keep that batter off its kilt. You want them to swing at a ball they think where it's going to be, but it's not. So he threw this curveball. Let's find out R. Since we're going to know what Y is, let's find out R is. We know what D is. Well, R is just going to be a radius. So this thing's going to be like a circle, a curve, right? And it's going to have a radius to it. So if we look at it that way, we know that in the acceleration in a curve is going to be what? Acceleration is going to be velocity squared divided by rho, which is the Greek for R, right? So we know that our acceleration is going to be our velocity squared divided by R, and this is what we're looking for. All right, we're looking for our R. Well, I know the velocity, but I don't know R and I don't know A, but I can get A from here, right? I can use simple F equals ma. Let's do that. So my acceleration is going to be velocity squared divided by R. Right? I know my acceleration because I know that force is going to be equal to mass times acceleration, right? The only thing I don't know is what's the mass of the ball. Well, generally, the mass of a ball, we call that slugs. The mass of a baseball is going to be equal to about 0.01 slugs. All right? Don't get too confused with slugs. Slugs are basically just the same thing as kilograms or kilos or whatever. It's the same thing. It's just a measurement of mass. It's just the American way that people in America, that's how they measure mass, because they use feet per second, which comes up with gravity's what, 32.2 feet per second squared, and the SI system is what, 9.8 meters per second squared, right? That's your acceleration. Okay, so we know, if we know the mass, we know the force is over here, we can figure out the acceleration. Yeah, that's going to be easy. You're just going to move the decimal point, what, up 2 places. So I know that R is going to basically, A is going to be equal to 20.2238 feet per second squared. Notice the slugs will cancel, right? The slugs cancel out. And when we put that over here, the slugs will cancel. You end up with feet per second squared. Hey, we know the acceleration. Now, don't keep this isn't acceleration of gravity or anything like that. This is the acceleration of the y direction. All right, this is the acceleration of what's going on in the y world. All right, when this thing is being thrown and it's gone into a curve like this, it's going to have an acceleration. That acceleration is coming from the fact that it's changing in position. This is the change of position in y. All right, not the pull of gravity. All right, so keep those two straight. All right, now we can find r, because we just put over r, we just bring our r over here. It's going to be what? Velocity squared divided by a, right? We know velocity squared now. We know a. So r is going to end up being velocity squared, which is 139.3 feet per second. And we're going to square that. And then we're going to divide that by our acceleration, which is 20.2238 feet per second squared. Oh, look at that. Our seconds cancel out, feet cancel out, you end up with just foot, and that's going to be amazing because that's what we want. So R is going to be actually a very large number. It's going to be 959.95 feet. So it's going to be this radius for this curve is almost 1,000 feet. I mean, it's almost 1,000 feet. So when you think about that, you know, to get that curve, the radius is going to be a very large radius because it's not curving that much. We'll see how much it curves here when we put this into y. So that would be our next step. Let's put this into y. Y is this going to be equal to, I'm going to round that up to 960, equals 960 minus 960. We're going to square that, minus 60.5, square that, and then we're going to take the square root of that thing. When we do the math on that, y comes out to be about 1.91 feet. So that ball moves from this side of the plate. When it leaves, it moves about 1.9 feet. That's about 22.8 or 0.9 inches. It's about right. And if you look at some of Joe Kelly's curveballs, some of them do actually move about 20 some inches off of the plate. The catcher's like way out here catching the ball, and the batter's swinging at nothing. The batter's either swinging above, below, or trying to hit the ball, but they don't. So this Y ends up to be about 23 inches, maybe a little less. I think the typical home plate is what, 17 inches? So you know this ball, this particular pitch that we're looking at, is going to be pretty far off, about 5 inches off of the plate, which is what you'd want. You know what I mean? That's what you'd want, and then you wouldn't want the batter to hit it. Very important. So let's look at this. Let's look at if we can put this into a time position equation. Let's see if we can put this path into a time position equation. We can do that. Let's think about each one of these dimensions. So I'll let you take a picture if you like. Okay, so I'm going to erase. So if we go to time position, let's look at it from two directions or two angles or two positions. Let's look at it from the side. If we're standing over here and looking at it from the side, we're going to see a pitcher's mound, right? You're going to see home plate over here somewhere, and then you're going to see the ball take a kind of like a, you're going to see the ball sort of like take that sort of motion in that direction, right? So it's going to kind of look like that. And we're going to say this is 4 feet. So the pitcher leaves the ball go at 4 feet, and we're going to say the catcher catches it about 1 foot. All right. I mean, that's pretty typical. I mean, I'm not saying that's exactly right, but anyway. So when we look at this, if we put this in the X and Y world, right? We put this in the X and Y world. This is going to be our RT. Our RT is going to be in here. We're going to want to know where this R is at each moment. As it goes down the field, this R is going to stretch out. As it's here, the R is going to be a little bit shorter. We know that times 0, the R is going to be equal to 4. So we know that has to be. So R of T is going to be what? In this is going to be our X direction, and this is going to be our Z direction. This time we're not going to use Y. Y is this particular direction. We used Y for the curve. So we're looking at it from the side view here. This is the side view. Really important. Remember, we're standing over here looking at it. All right, so we're going to see the ball sort of take that sort of motion. We know that in the X direction, we're going to have velocity initial times the time, right? And then we're going to have, this is going to be in the I direction. We're not going to think about the Y direction, so we're just going to 0 in the Y direction, so that's J. And then now, what do we do here? Well, we have this thing, we have gravity pulling this thing down. So this is going to be what? 1/2 GT squared in the Z direction. But we got to also realize that it's 4 feet in the air, so we're going to have to add that in there to make this a little bit larger. So R of T is going to be equal to velocity initial in our X direction. It's going to be 0 in our Y direction, or J direction rather, and it's going to be what? 4 minus 1/2 GT squared. Why am I using minus? Because we're going to say that in this direction our G is downward, so we're going to say it's G. All right, so we got that, but what about Y? Well, let's think about Y. If we look at it from the top, if we look down on this, we can see the Y movement. So if we look down on this, here's our pitcher's mound, right? Here's our home plate over here. So if we look down on this, you're going to see this sort of motion, all right? If that's the case, then we know this is going to be Y, and we know this is going to be X. We can play the same game. We can say, well, RT, in this particular case, is going to be what? Velocity initial T in the I direction, plus, well, it's going to be 1/2 AT squared, because this is an acceleration. We're talking about a Magnus force, so it's going to be an acceleration with T squared, and then plus 0, Z, because we're not worried about what's going on in the Z. We're just looking at Y and X right now. And that's not Oz, that's Z direction. 0 in the Z direction. Sometimes you can just put a 0 here like that, makes it a little bit easier. So now we've got our RT. We have I, we have J, and we have our Z directions. I'm sorry, this is Z. All right? So we just combine them. We just combine these two RTs, and we can get a time position equation for a fastball. Well, let's just do that. I'll let you take a picture if you like. Let's combine these two and make an equation for a fastball. In particular, we're going to look at an equation for Joe Kelly's 95-mile-an-hour fastball. All right, so my R of T, I know that in the X direction is the velocity in the X direction, velocity initial in the action, X direction. T, going to be in my I direction, plus what? Well, what's happening in X is in the Y direction. In the Y direction is going to be 1/2, right? My A in this is going to be force Magnus divided by the mass. So I know that force Magnus divided by the mass times T squared, right? Plus my H plus our 1/2, actually this would be minus, let's put it this way, H minus our 1/2 GT squared. And this is going on in our Z direction. So what we have found, what we've literally have found, is an equation that we can use to know about where, close to where, a 95-mile-an-hour curveball could be. R of t is equal to our velocity initial in the I direction times its time, plus 1/2 the Magnus force divided by the m, which is going to be an acceleration, times the time squared, time, or plus the how high it's left the pitcher's hand at what point, about 4 feet maybe, minus the pull of gravity, because the gravity is being pulled down, times the time squared. This particular equation will tell you where the ball is at any particular time. So if we put this time in here at 0.43 seconds, which is amazing that batters can actually hit a ball that they only have 0.434 seconds to realize they're going to hit the ball. If we put our time in here, and if you know the time, if you know the velocity initial, and you kind of know about the force Magnus, hey, you can pretty much know where the ball is. Anyway, so I hope that helps you, gives you a little insight into some fun stuff with Joe Kelly and the 95-mile-an-hour curveball. The next video we're going to look at is we're going to look at what the actual path is. We're going to find S. And S is going to be equal to what? dx dt squared plus dy dt squared plus dz dt squared, right? We're going to take the square root of that thing, right? So if we take the derivative of this, we take the derivative of that, the time derivative of that, we take the time derivative of that, we take the square root, and if we realize that ds, actually this is going to be ds is going to be equal to dt, right? We can figure out we can figure out this path. That would be the next video. And also, there's a nice little thing that you can think about, is that when the ball is being thrown, right? So here's the ball being thrown, and here's our R, right? R of t. Here's our R of t here. There's going to be an angle here, and usually it's called phi, right? Well, this angle changes as the ball moves. This angle also changes, so there's going to be a d phi dt, and that d phi dt can tell you the curvature of this particular pathway. So I'll show you how to find that, and I'll show you how to find the actual length of the ball that it takes, other than just saying that, oh, it's 60.5 feet. We will see that it's actually a little bit more than 60.5 feet because it takes an arced, curved path. All right, so that would be in part 2. All right, thank you very much. I really hope you subscribe. I do need a larger board. This board is just too small for the stuff that I'm going to get into. But anyway, it's working so far. I do hope you subscribe. Thank you.